Imagine you hire an expert advisor. They give you the perfect solution to every complex problem you face. But there's a catch. They absolutely refuse to explain how they arrived at that answer. Would you trust them? That is the exact dilemma we face with modern artificial intelligence. For a long time, machine learning didn't work like this at all. We built models that were entirely transparent. You could look inside and see every gear turning. Think of them as a glass box. Take linear regression. This animated 3D scatter plot shows how these older models work. You take an input, multiply it by a specific weight, and you get an output. It draws a single straight line right through the center of your data. The math is simple, and the results are entirely predictable. Because you can follow the math step by step, you know exactly why the machine made its decision. If it makes a mistake, you can audit the process and fix it. That transparency builds trust. But reality doesn't always line up neatly. Things humans do without thinking, like recognizing a face or translating a sentence, involve messy, complicated data. This plot shows the XOR problem. Two categories sit on opposite corners. If inputs match, it's 0. If mixed, it's 1. Notice how a single straight line cannot separate them. A linear model tries slicing from every angle, but fails every time. In 1969, critics argued that if a system couldn't master a basic 4-point logic gate like XOR, it would never navigate the high-dimensional reality of human speech or vision. This specific mathematical failure was so high-profile that it effectively choked off research and funding for the entire field for years. Solving the problem required a shift away from single straight lines. To move forward, we have to stop forcing the world into a glass box and build systems capable of handling non-linear data. Instead of manually writing features and rules, researchers looked to biology. They designed a system loosely inspired by the human brain to figure out the rules on its own. This diagram shows a feed-forward neural network. Data enters through the input layer on the left, travels through the middle sections, and produces a final prediction at the output layer on the right. Let's zoom in. In the forward pass, an incoming data point like x1 is multiplied by a specific weight assigned to that connection. Notice how the pathways representing weights W1, W2, and W3 all converge into a single node in a hidden layer. Inside this hidden node sits an activation function. It acts as a gatekeeper, taking the sum of those incoming signals and applying a nonlinear math equation to decide whether the signal is allowed to pass forward. When you stack hundreds of these nodes and layers together, you create an escalating chain reaction of mathematical functions. By forcing the data through these hidden, nonlinear layers, the network gains the ability to discover its own features. It identifies the best ways to transform complex information without a human telling it what to look for.
But this raises an obvious mechanical question. If humans aren't programming the exact rules, how does the network know which weights to assign to those connections in the first place? At first, it doesn't. A new network starts in a state of chaos, guessing weights entirely at random. Naturally, its initial predictions are completely wrong. To fix mistakes, the network uses backpropagation. It calculates the error and sends that information backward through the system. By rapidly looping forward to guess and backward to correct, it uses calculus to adjust every single weight, inching closer with every pass. Repeat this iteration millions of times, and the machine shapes itself to fit the data, mapping out the hidden rules entirely on its own. We provided the data and the architecture, but the system is autonomously teaching itself the right answer. We have removed human intervention from the internal logic completely. This architecture allowed machine learning to successfully navigate the limitations of the past, matching human performance in vision and translation. But that capability came with a steep cost. By relying on hidden layers to figure things out for us, we traded interpretability for raw power. We built a black box. When a network has millions of parameters constantly adjusting each other across dozens of hidden layers, the math becomes too dense. A human brain simply cannot track the logic from input to output anymore. This opacity becomes dangerous when we deploy these models in high-stakes environments. If a network denies a loan, makes a medical diagnosis, or predicts criminal recidivism, we need to know why.
With a black box, we cannot be sure if the network actually learned the true rules of reality, or if it just exploited a biased shortcut hidden deep inside the training data. This scatter plot shows another major flaw, called overfitting. Because neural networks are so highly flexible, they risk rigidly memorizing the exact training data rather than understanding the broader underlying concept. Factor in the massive amounts of computational time and energy required to train millions of parameters, and the costs start to compound. That leads to a foundational rule in machine learning. You should never deploy a complex neural network until you have tried to solve the problem with a simple, interpretable linear model first. Deep networks can now map input vectors to outputs across tasks that were once considered exclusively human. But because that mapping happens through millions of self-adjusted parameters, the resulting logic is harder to explain than any algorithm we've ever hand-coded. And it comes with a delicate mechanical challenge. Backpropagation tells the network which direction to adjust its weights, but how does it know how big of a step to take? Step too far, and you overshoot the answer. Step too little, and you never arrive.